So this will be our last lecture in second module. We have one more module to cover, and we must be fast. So I think there is one word, one important technical term idea of which I described very carefully, but I did not use that technical term. So I think I should spend some time on that. In the last lecture, we talked about transformation of stresses and how we can use Mohr circle to get help with to help on how to calculate shear stresses and normal stresses in different planes. So in a 2D case, we usually have two normal stresses, sigma x and sigma y, and a shear stress value tau xy. For that, we figured out that we can actually use a circle whose center is lying on an x-axis, and here y-axis will represent shear stress and x-axis will represent normal stress. And we also figured out that positive shear stress acts downwards if we use the exact formula we found out by derivation. I've seen that there are some people who use positive to upwards and a different formula. I don't well, for this course we will always follow this convention, and make sure that you follow it too when you are writing exams or submitting assignments. Make sure that you follow this convention, positive to downwards. So now we know that, just a second, I'll take that. So to continue, so we know that for a particular plane, we considered a general case with stresses sigma x, sigma y and tau xy. We rotated the plane of interest. We rotated the coordinate system by a certain angle, and we found out the normal stress values and shear stress values for the new coordinate system. So this coordinate system can actually be represented by a diagonal. Here when you mark this point AC, can be thought of as this diagonal can be thought of as representing the principal plane corresponding to sigma x, which is the not principal plane, the plane corresponding to sigma x. And A dash C can be thought of as the the plane on which sigma x dash acts. So when you continue to change the coordinate system, what is the maximum possible value that sigma x can have? Means what is the maximum possible value normal stress can have? What is the maximum possible value shear stresses can have? These things we have already discussed these things, and we found out the values also. And using geometry, this is now much easier. The maximum value will be here for normal stress, minimum value of normal stress will be here, maximum value of shear stress will correspond to the coordinate system where diagonal of the circle is drawn parallel to y-axis. So I talked about all of these things in the last lecture, but now I am revisiting the entire thing only to make sure that I introduce this term called principal stresses and principal planes clearly. So principal stresses are the maximum and minimum value of normal stresses, and principal planes are the planes on which the principal stresses are acting. Let's say this is our Mohr circle, and on x-axis you have normal stresses, and there is always a diagonal which represents a plane which has certain value of sigma x, and on the plane perpendicular to it you will also have sigma y acting on it, and corresponding shear stress value will be here. So when this diagonal is continuously rotating, maximum value of sigma x happens here and the minimum value happens here. And you can see that you know that when you have theta rotation of the coordinate system, you will have 2 theta rotation of the diagonal here. So maximum values of normal stresses, maximum and minimum values of normal stresses are separated by an angle 180 degree. So the coordinate system or the plane will be mutually perpendicular to each other, which means 90 degree apart. Maximum value of shear stress will be equal to the radius of the circle. So these planes on which the maximum and minimum normal stresses occur are known as principal planes, and these maximum and minimum values of normal stresses are known as principal stresses. And you also have a plane or plane where maximum value of shear stress is acting, remember that that's not the definition of principal plane. Principal plane means maximum, the planes on which maximum and minimum values of normal stresses occur, and they are usually separated by an angle 90 degree in the 2D case. In the 3D case, that becomes a little more complicated. Let's see if we can talk about that also. Also remember that we had derived equations for finding out principal stresses. We just call them sigma max and sigma min. So these are the principal stresses. You can also remember this formula using our Mohr circle. how do we do that? I talked about in detail in the derivation how we get this Mohr circle, but just to remind you, let's say this is our Mohr circle, and here you have the normal stress, and here you have shear stress, positive downwards and negative upwards. And let's say you're given a system with a certain sigma x value, sigma y value, and tau value, and from that you need to find out the principal stresses. So you can directly use the equation. So here I want to tell you how that equation came out from the Mohr circle clearly, so that you can easily remember the equation. Now if this is sigma x and this will be sigma y, this is the plane representing our current coordinate. So the principal stresses are the maximum and minimum values of stress. So the maximum value will be here and minimum value will be here. So to get there, we need to rotate this by a certain angle. But if you are only being asked to find out the principal stresses, what you can do is you can calculate this length. This total length will be equal to, sigma 1, which is maximum value of normal stress, and this length will be equal to minimum value of sigma normal stress. Now this let's take the example of sigma 1. Sigma 1 will be equal to this length from here to the center of the circle plus radius. That will be the value of sigma 1. Distance from here to the center of circle minus radius will be the value of sigma 2. So let's just say, so sigma 1 is equal to, let's say this point is C0, where C is the x coordinate, C0, and R is the radius of the circle. So C plus R will be sigma 1 and C minus R will be sigma 2. But what is C here? C is the center of the circle, so C will be equal to sigma x plus sigma y by 2, right? So this is the diagonal. So the middle of the diagonal can be found out by averaging sigma x and sigma y. And what is radius? This is the radius. How do we find out the radius? If this is sigma x and this is sigma y, so this is tau value, right? And that is equal to this length. So now we want to write radius. This is the radius of the circle, and this height is tau. And what is this length? That will be this minus this, right? Sigma x minus sigma x plus sigma y by 2. And that will be this length. So square of this length plus square of this length will give you the length. Using Pythagoras theorem, you can calculate this r. So this plus r will be equal to sigma 1. So if you compare it with our equation here, you can see that we've used sigma x minus sigma y by 2, right? Sigma x minus sigma y by 2. So that will be equal to nothing but sigma x, right? Same thing, right? This length will be equal to sigma x minus sigma x plus y by 2 is nothing but how do you subtract 2 into 2? Sigma x minus sigma y by 2, right? So this is sigma x minus sigma y by 2, and this is tau. So diagonal will be equal to sigma x minus sigma y by 2 whole square plus tau square, tau xy. Okay, I did not write xy, tau xy. So C minus R will be equal to the same things, sigma x plus sigma y by 2. Instead of plus, you will have minus here. Sigma x minus sigma y by 2 whole square plus tau square. So this is how you should remember the equation. Don't try to memorize it. Center of the circle will be sigma x plus sigma y by 2. Plus, now we need to find out the radius. That will be square root of 1 length plus for the triangle, right triangle, 1 length square plus another length square, and one of the length will be tau, which is shear stress, and other length will be sigma x minus sigma y by 2. If these are sigma x and sigma y, sigma x minus sigma y to this distance. So this is how you should remember this equation. And these are nothing but our principal stresses. Now the same thing can also be done with strains. So you have learned the idea of stress and strain. Just the way we have drawn Mohr circle, we can also draw Mohr circle for strain. So before that, I'll just remind you the definition of strain. So there was a difference between strain tensor and definition of strain. So if you consider a 2D case, you must have studied it in first module. Strain here is defined as the gamma xy or gamma yx is equal to sum of these two angular changes. So that will be dou v dou x plus dou u dou y. So these u v's are like these are displacement v's, x displacement v's, y displacement. So when this a little element deforms to this shape, the strain is defined as sum of these two components. So you must remember the So this is our strain tensor. So in the tensor, we are actually using definitions of strain. We don't. The sigma xx is not actually linear. Sigma xx linear strain definition will not create any problem. Shear stress definition will have a problem. In the linear case, we don't need to sum up two components. That's not the right way to say it. Average of these two quantities will be used here in this strain tensor. So here epsilon xy will be equal to epsilon y yx, which will be equal to half of dou Ex plus dou Uy. But the definition of a shear strain is this one here, which is actually twice the value of this component used here in the strain tensor. So these shear terms should be replaced with gamma xy or gamma yx. So sigma xy is equal to gamma xy by 2. So this is something I just want to remind you this relationship. That's the only reason I talked about definition of strain here, because that will make a difference. That is the only difference between stress, Mohr circle for stress and Mohr circle for strain. I'll find out a suitable figure. So like I told, the strain, Mohr circle for strain will be very similar to Mohr circle for stress. So the only thing you need to remember is the relationship. So the linear strains are the same. You don't need to write x twice. You can avoid it if you like. So it will be etc. So same thing. Okay. So you have this. So this is the shear strain. So when we draw the Mohr circle for strain, it's going to be very similar to that of stress, but the only difference here is that for the shear component we are using a half, and we have to use that half because of our definition. Other than that, everything else will be same. So how can we write down equations for different components? Let's say we have a given system where shear strain values are normal strain values are sigma x and sigma epsilon x and epsilon y, and you have shear strain gamma xy. And if you are rotating the coordinate system by a certain angle, what will be the new value of normal strains and shear strains? So just like the previous equation, the only difference is that we replace stress. So even the derivation part would be quite similar to that of stress. So I'm not going through the derivation and other things in detail. I'll just write down the final equation. So if we rotate the coordinate system by an angle theta, the new value of normal strain will be epsilon x plus epsilon y by 2. I think if I remember the equation correctly, it's minus here or plus. I forgot. Okay, sigma epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy sin 2 theta. Yeah, forgot about the half. That's why I talked about the half in the beginning. The half must be there. So for the shear strain for the rotated coordinate system will be, okay, I think this is plus. Yeah, of course that is plus. Yes. Sigma x minus epsilon y by 2 sin 2 theta plus gamma xy by 2 cos 2 theta. So that is correct. So here minus will come when you are calculating the y component, epsilon y dash. So this will be the equation. And for principal values, the maximum and minimum values, again the very same equation can be used, just like the case of stress. So maximum value epsilon 1 or 2 will be equal to, remember what I told you to how do you remember this equation for principal values? Think about the triangle here and think about finding out the maximum and minimum values by adding radius from C and subtracting radius. So center will be equal to epsilon x plus epsilon y by 2 plus or minus depending on it's 1 or 2, right? Epsilon x epsilon minus y by 2 will be one length of triangle square plus, and the second length will be half here. So this will be the maximum and minimum values of strain. Maximum and minimum values of normal strain. And for maximum and minimum, for maximum value of shear strain also, we can write the equations similar, just the way we use it for stress. What else should we discuss here? Here okay, what will be that quantity here? That is maximum value of strain will be equal to that radius part, which is sigma epsilon x minus epsilon y by 2 whole square plus gamma xy by 2 whole square. This will be the magnitude of maximum shear strain. And here, yeah, negative will be there, which we deal with by inverting the coordinate system in the y-axis. I forgot something here. This is a half here also. So just make sure that you don't forget about the relationship between components of strain tensor and the definition of shear strain. This half should always be there. Here also I think I forgot half. Yeah, it's okay. Everywhere you should have that half. Now let's derive a relationship between some elastic constants. Young's modulus, shear modulus, and Poisson's ratio mu. Young's modulus is also known as a modulus of shear modulus is also known as modulus of rigidity. Shear modulus. And Poisson's ratio. So first of all, let's consider a case of pure shear. What is pure shear? Pure shear is the case where you only have shear stress, pure shear, no linear stresses. How will that look like in a Mohr circle? If Mohr circle is here, wherever you keep the diagonal, you will always have some value of normal stresses. How do we make the normal stress 0? Only one case will, only one state of stress will give you that case. Let's say center of the Mohr circle coincides with the origin, and you represent the tensor by considering planes corresponding to this diagonal, right? For this diagonal, sigma values, x coordinates will be 0. and tau will have the maximum, shear stress will have the maximum value. So this is the case of pure shear. So in the case of pure shear, we can convert the case of pure shear into a case where you have only normal stresses. So if you rotate your coordinate system by 45 degree, then you will have to rotate the diagonal by 90 degree. Then you have a system where principal planes are obtained using this diagonal. So in this case, there is no shear stress because y coordinates are 0, but you have values for sigma 1 and sigma 2. Sigma 1 will be equal to tau, right? Because this is the sigma is equal to radius of the circle. Radius of the circle is equal to maximum value of shear stress, which we will get in the pure shear case. So that value is taken as tau. So sigma 1 is equal to tau, sigma 2 is equal to minus tau. So this, if you rotate the coordinate system, and bring it to such a case, here you will have sigma 1 which is equal to tau, and sigma 2 which is equal to minus tau, right? Minus tau. So its direction is opposite. So I'm not simply writing negative to show that. So this one is tau, this is also tau, right? So this is where we begin. Now let's consider an infinitesimally small element within a structure, and let's say it is being deformed. So this was the original diagonal. After deformation, this is the new diagonal. Let's say A is the dimension of the, let's say this is a square and A is the dimension, and shear strain is defined as the angle by which, angle in radians by which the element get distorted. So if this length is A, using in radians we know that angle is equal to tangential the part of circumference, the arc length divided by radius. But here you don't have a circle. If this is infinitesimally small, this deformation is exaggerated. So you have to actually assume that this is this angle is very close to 45 degree, right? This is grossly exaggerated. So for a very small deformation, this length will be A gamma, because gamma is equal to this length divided by A. Now Okay. Now we need to this angle 45, this is okay, 45, right? Close to 45, okay, close to 45. And also remember about our transformation which we talked about in the previous slide. So for a case of pure shear, was converted into a case of where you don't have shear stresses and have only normal stresses. So this direction, the linear strain in this direction can be called epsilon 45 degree, linear strain in this direction. Now we know that shear modulus is defined as shear stress by shear strain, and shear strain is equal to tau by G. But this epsilon is the component in the strain tensor. So that component can actually written like tau by 2G, because tau by G is the shear strain, and the component in the strain tensor will be half of that. Now this is actually equal to from generalized Hooke's law, we know that this is equal to sigma 1 by E minus mu into sigma 2 by E. This is an expression you are familiar with. Now here sigma 1 is the stress, normal stress in this direction. So when we convert our pure shear case into a case where you have only normal stress, sigma 1 value will be equal to tau. So tau by E minus mu, sigma 2 is equal to minus tau divided by E. So what do you get? Tau by E into 1 plus mu. So epsilon 45 degree is equal to tau by E into 1 plus mu, which is also equal to tau by 2g. Now just simply cancel out tau and write it in terms of E, Young's modulus. E is equal to, take 2g this side, 2g divided by 1 plus mu. So this is an important relationship for us. This is the relationship between Young's modulus, shear modulus and Poisson's ratio. One clarification here, I directly wrote epsilon 45, which is the linear strain, equal to tau by 2g. How did I do that? I think by mistake I told strain component in strain tensor is equal to simply half of this one, and that is true. Component in strain tensor will be equal to, for the shear values it will be equal to half of shear strain, but that is not actually equal to linear strain in this direction, right? This is nothing but linear strain in this direction. So I had to actually prove that. That's the reason why I wrote this. I think I kind of skipped it. So we have to prove that epsilon 45 is actually equal to gamma by 2. How do we do that? For an infinitesimally small deformation, gamma, this length is a gamma, just like I told. So if you take this small triangle here, this length will be equal to a gamma by root 2, considering that this is 45 degree, right? This is 45, that is 45, a gamma by root 2 will be this length. This cannot be 45, but assume that this is very close to 45. Now the length of this diagonal will be equal to root 2a, right? If a is the side length, so diagonal must be equal to root 2a. So in that case, epsilon 45 is equal to change in length, which is a gamma by root 2 divided by total length or original length, which is a root 2. A root 2 is the total length of diagonal. It's actually changing a little bit, but assume that this deformation is very small. So change in length is this one, which is a gamma by root 2 divided by original length, which is a root 2. Now this is equal to gamma by 2. So that is the reason why, this is the reason why we simply took epsilon 45, which is linear strain, as tau by 2g. I kind of skipped a step. This is the step. You actually have to prove that epsilon 45 is equal to gamma by 2. Otherwise you can't directly write this relationship. So with that, I conclude this session. and I actually announced that I'll conduct a quiz by the end of the week, which I will do. So for the quiz I will include everything I have taught you so far, including this one. So I'll give you more details in your group. So I'll conclude it here.